Hi, this is Dr. Bricker here with some information for the final exam. So the final exam will be something between 20 and 22 questions. And if I were to study for this, I would definitely watch this video, go back over the 3 exams that we've had, also go over the 3 practice exams, go over the homework, and look back at the notes. Lots of information here, but I think that's the path I would take. If you think about it, there's probably about 15 chapters or something and 20 questions, so at most there's 2 questions per chapter. Usually there's probably about 1 question for each chapter. So let's get started. Again, multiple choice just like the other tests, but you have to show your work. Chapter 1 was just kind of an introductory chapter. We talked about motion diagrams. Chapter 2 is where we got into kinematics equations and some graphs. The first lab we did, Activity A, actually dealt with that. You were part of the experiment. So make sure you know what different things mean. Like, for example, in an x versus t graph, what does this correspond to? What can you tell about this motion? This is where the velocity is actually 0. Here's another example. This is constant velocity here. So the rate of delta x over delta t is constant. And again, if something is speeding up, it might be something like this. And you could look at the slope of the tangent lines here to figure out the speed. So the slope here is positive. If we had something like this, here the slope would be negative. So positive velocity, negative velocity. Here actually 0 velocity. Okay, so that's just the velocity versus time graph. We also had velocity, sorry, this is a position versus time graph. We also looked at velocity versus time graphs. So go ahead and take a look back through those. Make sure you're familiar with how to represent what's represented in different graphs, and you'll see one of those on the test. The other thing from chapter 2 were all the kinematics equations. So velocity final is equal to velocity initial plus at. So these are all for constant acceleration. Final velocity squared is equal to initial velocity squared plus 2a delta x. This is just all, I'm writing these all in the x direction. It could be for the y direction as well. And then finally, delta x, initial velocity times time, plus 1/2 at squared. So I'm sure you'll see a kinematics question on the test as well. Related to this is free fall. So remember, free fall, and I'm going to put fall in quotes, means just under the influence of gravity. So in that case, the acceleration in the y direction, negative 9.8 meters per second squared. And then you can go back and use all the kinematics equations we have here. We're talking about the y direction though, and you know the acceleration in the y direction. So many times free fall problems won't specifically say this is the acceleration, but if you're in free fall, this is the acceleration. We're assuming there's no air resistance. Okay, so next was chapter 3, which was 2-dimensional motion, and the part that we covered in this chapter was projectile motion. So not only do we have motion in the x direction, we also have motion in the y direction. So you have to look at those things separately. So it might be something like this. You launch something at some initial velocity and some initial angle, and maybe you want to figure out how far it flew, different things like that. So here's theta. This is going to have an x velocity that's not going to change, and it's also going to have a y velocity. The y velocity actually changes. The x velocity the whole time stays the same. The y velocity starts out with whatever it is. At the highest point, the y velocity is 0, and then continuing back on. But again, it's the x part that doesn't change the whole time. Okay? So we really looked at breaking vectors into components in this chapter. So from this picture, you know that the x velocity is v0 cosine of theta, and then the y velocity initially is v0 sine theta. So we did several different problems involving projectile motion. We did a projectile motion lab. The thing to keep in mind here, at the highest point, this is where the y velocity is 0. So you could exploit that fact to figure out how high you go. Again, we're going to use all the kinematics equations that you just saw. It's just that we're going to look at them in the y direction. So all of these that we just went over, you could just put a y here, a y here, y here, same thing here. This is all for the y direction. Maybe I can change that into a delta y. Same thing here, delta y, initial velocity in y, acceleration in y. So for the y direction, we have all of these. Sorry, y direction. We have all of these. So there's a lot of resources there for us. In the x direction, the only thing that you have is this. X velocity, delta x over delta t. Okay, so here's a nice picture that goes along with it. Y direction, you have all the kinematics equations. X direction, we really only have this. Here's how you break vectors into components for this situation. And if you remember, this was a specific situation where we could figure out this distance called the range. And the range, initial velocity squared, this is the overall velocity, so maybe I should just leave it like this. The overall velocity squared, sine of 2 theta divided by 9.8 meters per second squared. So this will give you the range, just knowing the overall velocity. Actually, to clean up the notation, maybe I should make that back into V0. This is the overall velocity here. I used V0 here. This is V0 here. Okay, let me sneak the V0 back in there. Okay, again, but this is the overall velocity. This is the X part. This is the Y part. So I'm sure you'll see a projectile motion question on the test as well. Okay, the next thing we saw was Chapter 4, which Chapter 4 is actually titled Forces and Newton's Laws of Motion. We started by looking at free body diagrams. And we saw that it's not just for fun, it's an actual great picture to represent what's going on. So make sure you're familiar with free body diagrams. You just put the forces acting on an object, and usually you represent the object by just with a dot. So for example, if I'm pushing a box across the floor, this could be the applied force. Maybe there's friction back the other way. Here's the weight, and we saw that that's equal to mg, and then the normal force. So there's a free body diagram. In this picture, if I wanted to figure out the acceleration, I could use Newton's second law. So you add up all the forces, that's the net force. It gives you something. It gives you ma, and then you have to supply all the forces. So if I'm looking at this horizontal acceleration, here the normal force, weight are equal to each other. There's no acceleration. Vertically, the forces are balanced. There is an acceleration horizontally, though, because this is bigger than that. So I could put applied force minus friction, and then, depending on what I'm given, I could solve for different things. So make sure you know how to construct a free body diagram and also use Newton's second law. It seems so easy, maybe, net force ma, but it's definitely not easy. This is what makes it hard. You have to supply the forces that go here. Okay, good. I guess the other thing I would add, there's 3 laws from Newton. This is Newton's second law, the only one that actually has an equation. The first law, if you remember, an object in motion stays in motion unless acted on by some outside force, kind of related to the second law, actually. So if the acceleration is 0, that means the change in velocity is 0. So an object in motion will just stay in motion. If it has some velocity, it's already moving, it'll continue with that velocity unless there's something to change it. On Earth, that's the one that doesn't really seem like it's true because we always have friction on Earth. But if you're in outer space and you throw, say, a basketball or something and there's nothing around, the basketball will just keep going. Of course, it accelerates when you first get it going, but once it's moving, it will just keep moving. And then the third law is the action-reaction idea. I push on the wall pushes back. That sort of thing. So the first law and the third law really help us get some additional information to go back to the second law. Okay, great. Okay, then we hit Chapter 5. So we're getting close to the information that was on the first test. Chapter 5 was an application of Newton's laws. So everything that we did in Chapter 4 applies. We just have some additional cases to look at. We looked at an object on an incline. So if this is theta, this is some kind of object here. We saw that this is the normal force. This is mg. And you can break mg into its components. And we saw if this is theta, this is back to being theta. The part down the incline turns out to be mg sine theta. And then this part here is mg cosine theta. And then if it's not moving, maybe there's friction back the other way. So in the picture, you can see the normal force is equal to mg cosine theta. And again, if it's not moving, mg sine theta is bigger than friction. If it's accelerating down the incline, though, mg sine theta must be bigger than friction. And we looked at it kind of like this, x and y. So that was one big application from Chapter 5. Again, make sure you at least skim through Chapter 5, look over the homework associated with that. Another thing from Chapter 5 was this idea of friction. So there's two different kinds of friction. Static friction, less than or equal to the normal force times mu sub s, the coefficient of static friction. And then we have kinetic friction. That's equal to the normal force times mu sub k. So this is the friction that happens when something's moving. This is the friction before something starts moving. So less than or equal to the normal times mu sub s. It's only as large as it needs to be. So in many problems, what we did was to figure out the maximum amount of static friction. That's when it's actually equal to the normal force times mu sub s. So look back at the practice test and the actual test. If you remember, we had a problem where you apply a force. How much is friction? Well, the first thing you have to do, and this will be more familiar when you look back at the practice test and the actual test, figure out the maximum amount of static friction. If the static friction is greater, the maximum static friction is greater than the applied force, then you're in the static friction regime. If the applied force is bigger than maximum static friction, then you're in the kinetic friction regime, and you can do the appropriate calculations from there. So take a look back at that. You'll see something similar to that on the actual test. Okay, so then we started skipping around a little bit. We went to Chapter 9, which was on momentum and impulse. And there are two genres of problems from Chapter 9. It really goes back to the impulse relationship. So impulse is J. It gives you the change in momentum. So it's just another word for change in momentum. And that's equal to F times delta T. So what you get from this is final momentum minus initial momentum, mv final minus mv initial, m times delta v. Several different ways of writing it. So if you're given a problem again with force, time, mass, and velocity, you can go back to the impulse relationship to solve that. These are the sort of problems like a baseball bat is in contact with the ball for a certain amount of time. If it comes in with a certain velocity, what's the final velocity? And these are velocities, so it could be positive or negative. If you're going one way and you say it's positive, going back the other way has to be negative. So take a look back at the practice test and the actual test to refresh your memory on that. So this is the kind of problem where there is an outside force. So let me actually write number 1 here. The second kind of problem is there is no outside force. These are collision problems. So no matter what kind of collision you have, the initial momentum is equal to the final momentum. So we did a few different kinds of collisions. So again, look back at the actual test, the practice test, the homework. So whenever there's a collision, things are colliding, cars are running into each other, that sort of thing. You set it up as the initial momentum is equal to the final momentum. And then you have to actually write down the momentum before, write down the momentum after, and keep track of the signs. If you say one way is positive, the other way has to be negative. So this is probably a chapter where you'll see a couple of problems. I'm sure you'll see this impulse relationship type problem, and you'll also see a collision type problem. We had a couple of different sorts of collisions, the stick together kind, and also, just the general kind. So again, take a look back at those. After Chapter 9, we went on to Chapter 10. This is the energy chapter. So a couple of ideas here too. And this chapter is actually called Energy and Work. So we saw the work-energy theorem. So work, so I use the big W for work to keep it from, distinguish it from weight. So this is F times delta X. And what does it give you? The change in kinetic energy. So kinetic energy initial minus kinetic energy final. And kinetic energy, if you remember, is 1/2 mv squared. So these are the kind of problems if you're given force, displacement, mass and velocity. You can use the work energy theorem to solve this. The thing about this is you have to figure out the part of the force that is lined up with the way that you're moving. So when you read back through the chapter, it might actually even say something like F, and I think they called it D cosine theta. So what does that actually give you? Let's take a look at just a little picture here. If this is the force, and this is the distance you're moving through, I called it D here, I called it delta x here, it's the same thing. The part of the force that's lined up with the way that you're actually moving, if this is theta, this part here is F cosine theta. So you have to figure out the part of the force that is in the same direction that you're moving. So here the work is actually positive. You're going this way, the force is this way, work is positive. On the other hand, if you had friction back the other direction, you move this way, friction's back the other way, the work by friction would be negative. The work by friction is always negative. So just remember that work could be either positive or negative. And the use of this is, again, if you have force, distance, m and v, you can figure out, whatever you're missing from the given information. So it's a clue, though. Given these things, maybe you should go with the work energy theorem. The other kind of problem from chapter 10 was conservation of energy. So the initial energy is equal to the final energy. It could just change forms, and we have these different sorts of energy. Kinetic energy was 1/2 mv squared, gravitational potential, mgy, spring potential, 1/2 kx squared. So you'll definitely have an energy conservation problem. We did problems like, I call it the Aldi's problem. A shopping cart's moving with a certain amount of kinetic energy, hits a spring, all that kinetic energy becomes spring potential energy, that sort of problem. We also looked at the roller coaster type problems. You start on the top of an incline. This will bring back some memories from the second test. You start up here, it's all gravitational potential energy. Initially, you get here, you still have gravitational potential energy, but now you have kinetic energy. So this energy here would be equal to this energy here. Maybe I should put final here. And you don't have to start from rest up here. Maybe somebody gives you, you're already moving, or somebody gives you a push. But this total energy is equal to this total energy. It's just changed forms. Okay, and then we went back to chapter 6, which is circular motion. Another title for this chapter could have been The Search for the Force Towards the Center. That's what I kept talking about. And we do have an acceleration here. It's v squared over r. The reason we have an acceleration, even if you're going at a constant speed, is the direction keeps changing. I always give the example, if you have your child and you're spinning them in a circle by holding their hands, and you let them go, they would fly off in the same direction they were moving. There has to be a force on the child from you, towards you, so towards the center of the circle, that keeps them going in a circle. So there's always got to be a force towards the center. This is called centripetal acceleration, and it's, again, towards the center. And this is what we always did. Add up all the forces. It's ma. That's going back to chapter 4. It's just now we have a certain kind of a, the centripetal acceleration towards the center. And again, you have to fill in whatever goes in this box here. What is the force towards the center? Just to refresh your memory a little bit, if you go through this, little bit of a valley in your car, you're going through part of a circle here. You have a normal force this way, mg this way. I purposely drew the normal force bigger than mg. There has to be a net force towards the center of the circle. So I can say, add up all the forces, it's ma. We have mv squared over r here. R is the radius. And then again, you have to fill in what goes here. And I would put normal force minus mg. So in this problem, we have mv squared over r plus mg is equal to the normal force. So when you're going through this valley part here, the normal force is actually bigger than it would be if the car was just resting there. So you'll definitely see a circular motion problem. Again, look back at the homework, the practice test, the actual test, and you'll see we did several kind of problems, going through this part. I'm not saying it's going to be this specific question. We did going through the top of a loop on a roller coaster. We had like a ball on the end of a string going in a horizontal circle. So take a look back through those. Make sure you know this concept, though. That basically was the second test. Okay, again, so the main focus of the second test was momentum, impulse, energy, circular motion. That was the big focus of the second test. And then the third test information, which is probably fresher in your mind, dealt with beginning with rotational motion. So rotational motion is an object rotating on its own axis. So this object is rotating this way. It's not going anywhere, it's just rotating on its own axis. So the big idea here was, first we had to come up with some variables to describe this. So instead of delta x, we had delta theta, measured in radians. And then we had angular velocity, so that's omega, radians per second. And then alpha, angular acceleration, radians per second squared. And we had the whole set of kinematics equations that go along with this. So for example, omega final is equal to omega initial plus alpha times t, omega final squared, omega initial squared, 2 alpha delta theta, and then delta theta initial omega times time, 1/2 alpha t squared. So there's a nice symmetry between this rotational world and the linear world. Here's a couple of things that related these back to each other. Linear velocity is equal to angular velocity times r, and then also regular acceleration is equal to rotational acceleration times r. So these are the couple of keys to go from the rotational world back to the linear world. So the next question is, well, what's causing this angular acceleration? So just like the linear world, a net force gave you an acceleration. In this rotational world, a net torque would give you an angular acceleration. So torque plays the role of force. Rotational inertia plays the role of mass. So it's more complicated, though. It's not only mass, but how's the mass arranged? What's the shape? And then alpha here plays the role of A. So this is rotational inertia, moment of inertia, same thing. And just like the third test, I will give you the rotational inertias. You don't have to write down the whole group of them. Okay, so net torque I alpha. So what exactly is torque then? Well, let's take a look at maybe something like this. This was from the practice test. Actually, the practice test, several homework questions. The practice test, the third one, we had a force here at some distance here, R1. So this torque one would be F1, this is just the magnitude of it, times R1. Technically it would be negative because it's going clockwise. And also on the practice test, I think we had a force 2 over here at R2. So then torque 2, let me actually put the minus sign in there just to make it clear. Torque 2 would be F2 times R2. And then you can figure out the net torque, and that actually gives you something. It gives you I alpha. So over here, you could do the same thing. This would be F2 R2 minus F1 R1. Okay, and then you could figure out whatever you're looking for. The actual test, I didn't make it as complicated as this one. I actually gave you what the net torque was on the actual test, and then it was I times alpha. Again, it's always a little more complicated because in general they'll give you the mass and the radius and the shape, and you have to calculate I. So you'll definitely see something from chapter 7, probably going along these lines. Coming right after chapter 7 was chapter 8, equilibrium and elasticity. So equilibrium means you add up all the torques, it's equal to 0, add up all the forces, it's equal to 0. This is a fancy way of saying all the torques are balanced, all the forces are balanced. So take a look back at problems from the practice test and the actual test with balancing torques and forces. The actual test was the problem where it was a sign that was being balanced. It was something like this. This was tension, this was mg, this was L over 2 out to here, and then the whole length here was L. So by balancing torques, I mean this tension has a part in the y direction, part in the x direction. So Ty, and then where it's acting, L, that's the torque because of the tension, has to be equal to mg, and then where it's acting, L over 2. And then you could figure out what the tension in the y direction was. That was on the actual test. Look back to the practice test. The practice test one was a neat one as well. It was somebody holding a shot put in their hand, and we wanted to figure out the force of the muscle. So you'll see something similar to this or the one that was on the practice test. So make sure that you're familiar with, how to balance torques. It's not only the force, but where is the force acting? And again, I picked this as the pivot point for this problem. So all the torques about that point are balanced. Okay, great. Oh, and a little bit about elasticity. This went back to this relationship. Area, Young's modulus, delta L over L. So be familiar with this idea. The practice test and the actual test just had a 5-point question on it. How do strings stretch under different loads, things like that. So in this formula I have here, A here is the cross-sectional area. This is the length. Delta L is how much it stretches, and Y here is Young's modulus. So all different materials have different Young's modulus. And then F is the force that's actually stretching the string, or, whatever it is that you're stretching. Okay, then we moved on to simple harmonic motion. That's what SHM stands for. So with simple harmonic motion, it boils down to this. And again, we'll focus on the mass on a spring. The period is 2 pi square root of m over k, or the frequency, if you want to do it like that, 1 over 2 pi square root of k over m. So if you know the mass on the spring and the spring constant, that's what k is here, you can calculate the period. And we had one of those on the actual test, similar one on the practice test. So just be aware of that. If it's simple harmonic motion, immediately you know this happens. Also with simple harmonic motion, a couple of pictures come to mind. I'm running out of room here, so let me go to another piece of paper. Okay, so here's a spring. It starts out here, where x is equal to 0. And what we've always done is pull it out here to x is equal to a. So this is the amplitude, this distance. And then you let it go. It oscillates over here. So the magnitude here is also a. So here, all of the energy is spring potential energy, 1/2 Ka squared. Here's the kinetic energy is equal to 0. Same thing over here. The mechanical energy on this endpoint, 1/2 Ka squared, kinetic energy equal to 0. That means the speed must be equal to 0. Same thing here, speed is equal to 0. Equilibrium position, this is where the spring potential energy is 0. So all of the energy here is just kinetic energy. And really it's the maximum amount because the spring potential energy is 0 here at the equilibrium position. So this is where it's actually moving the fastest also. So V max. Okay, here also the acceleration is equal to 0. The spring is not stretched or compressed anymore, so there is no acceleration. Here's where the acceleration is actually a minimum, the most negative, in other words. Here's where it's actually the maximum, over here at this point. Okay, and then the mass on the spring oscillates back and forth. In between here, the energy is made up of spring potential and kinetic. Here it's all spring potential, here it's all kinetic, here it's a combination. And same thing on the other side. Okay, and then related to this, but not exactly the same, was the idea of standing waves. And really I combined chapter 15 and 16 into just one lecture, and we focused on waves on a string instead of looking at waves in a pipe or something like that. And we saw that the speed is equal to the tension divided by the mass per length. So again, this is mass per length, this is tension. Period is involved here too. That's why the book uses F(t) for tension, just to avoid some confusion. Going back to chapter 15, we saw that the speed was the frequency times the wavelength as well. So these all work together. And then for standing waves, we also found the wavelength has to be 2L over m. And m here is the amount of antinodes. So if you have a standing wave that looks like this, okay, let me try to do this. These are all supposed to be the same size. You count the amount of antinodes, so here m is equal to 3. The amount of high spots, 1, 2, 3. And then you can figure out the wavelength. So it's 2/3 of this overall length. Okay, so this still works, this still works. So if I want, I can write this together like frequency times wavelength. That is the speed. It's equal to the tension divided by the mass per length. And then again, if you want to, you could put this in for the wavelength. Frequency 2L over m. That's equal to the tension divided by the mass per length. So one of the problems on the practice test, the actual test, was something like I gave you the tension, the mass per length, gave you the mode, that's what m is, the mode, and the frequency. Then you had to figure out the length that way. So this is kind of putting everything together here. Okay, if it's the fundamental frequency, fundamental means m is equal to 1. And then the harmonics are just multiples of that. So here's a way of writing this. So the second harmonic, so m would be equal to 2, is twice the fundamental frequency. The third harmonic is 3 times the fundamental frequency. So I'm sure you'll see some sort of standing wave problem similar to this. All right, and also for the third test, the final thing we did was fluids, the static fluids problem. Density, mass divided by volume. So you probably have seen that since like 3rd grade or something like that. The problem on the actual test was the mass of air in the room, something like that. So be familiar with that idea. We also did pressure at depth. This was also on the 3rd test. So the pressure down here, this is fluid statics again. The pressure down here, P1, is the pressure at the top plus rho g y, the density of the fluid. And this is the y that I'm speaking about here. So you can figure out the pressure at depth. The pressure up at the top, atmospheric pressure, 1.103 times 10 to the 5th pascals. A pascal and a Newton per square meter are the same thing, remember? Okay. I don't think I would do this to you, but just to remind you, 1 atmosphere is this pressure. Newtons per square meter, or pascals if you want to do it that way. The other thing in the fluid statics part was the buoyant force. So if you have something submerged in a liquid, maybe this is actually attached by a string or something like that. This is in a liquid, there's a buoyant force here. So if I wanted to be complete, okay, there's tension this way, there's the buoyant force this way, and then there's mg down. So if you try to weigh something, on a scale, and you have it submerged in water, this is really similar to what we did in chapter 4 and 5. The only difference is we've got an additional force called the buoyant force. So the buoyant force is the density of the fluid, the volume of the fluid that's displaced, times g. So you might have to take that into account. So in this specific example, we could balance these forces. We've got tension up plus the buoyant force, which is up. That's got to be equal to mg down. And then you can solve for the tension in this problem. Remember, when it's completely submerged, the volume of the object here, so the volume of this object, would be the same thing as the volume of the fluid displaced. So if this is 1 cubic centimeter, you put it in a fluid, the amount of fluid displaced is 1 cubic centimeter. It doesn't have to be completely underwater. It's just in this example it is. Or it doesn't have to be water even. It could be whatever fluid that you're putting it in. So on the actual third test, I put one of these pressure at depth problems and a density problem. So for the final, go back over the homework. Make sure you take a look at a problem similar to this one. I'm going to put a buoyant force problem on the final. Okay? Hint, hint to you. Also, what was not on chapter 13, we didn't cover it yet, was fluid dynamics. So fluid flowing through a pipe, for example. Could be something like this. This is the cross-sectional area. So the volume flow rate is the area times the velocity. and you could figure out the volume of fluid flowing that way. And this is, again, is the cross-sectional area. So if it's a pipe like this, the cross-sectional area would be pi r squared, or, pi d squared over 4. We can do a little bit more with this. For example, if you had a pipe or a hose, whatever it is, that gets narrower, we could figure out the speed at this side if you know the speed at that side, and you know different, the areas. So this is what I'm trying to say. If this is area 1 and we know the speed here, and you know area 2 here, we could figure out the speed over here. It's the continuity equation. The volume flow that flows through here has to be the same as the volume that flows through there. You're not losing any water, you're not gaining any water. So if those are the same, V1 times A1 is equal to V2 times A2. So this would be V1 pi r squared. This would be V2 pi r2 squared. The pi's cancel out, and you're left with this. Or you could do it in terms of the diameter as well. V2 d2 squared. Okay. Excellent. So we've got the volume flow rate. We know what that is. And if you're trying to compare one section to another, you have this situation. We also had Bernoulli's equation, and we did some examples in class. Maybe it even gets narrower here. So Bernoulli's equation was, let me call this pressure 1 and this pressure 2. Pressure 1 plus 1/2 rho V1 squared plus rho g y1 is equal to pressure 2 plus 1/2 rho V2 squared plus rho g y2. And this is V1. Again, this is area 1. This is V2 over here. This height would be y2. The height of the fluid here, maybe you could just say that this is y1. Up here, this is y2. So yeah, we did some examples in class, and I brought in a couple of different outside examples. An easier version of this is if it's a horizontal pipe and you want to figure out the pressure. So in a horizontal pipe like this, y1 is equal to y2. So it makes Bernoulli's equation a little simpler. I mean, this is the full version of Bernoulli's equation when you go from one height to the next. If you just have a horizontal pipe, y1 is equal to y2, this and this would cancel out. So it's a little simpler, a little smoother when you do that. Okay, so make sure you're aware of this volume flow rate idea and also Bernoulli's equation. Okay, great. Okay, and then the final thing, which wasn't on the third test, but we went over some problems in class. Chapter 12, Thermal Properties of Matter. And we started talking about the atomic model. So one atomic mass unit is 1.66 to the minus 27th kilograms. And then we looked at Avogadro's number here, 6.02 times 10 to the 23rd per mole. And it turns out if you know the number of particles, and using Avogadro's number, you can figure out the number of moles of a substance. So again, Avogadro's number is the number of particles, molecules, whatever it is. It's 6.02 times 10 to the 23rd per mole. Okay, so again, this is how moles, number of particles, and Avogadro's number are related to each other. Many times it's easy to figure out the number of moles if you know how much of a substance you have in grams. So if you take the mass of a substance in grams, divide it by the molar mass, and you can get the molar mass from a periodic table. So for example, oxygen, look in the periodic table, you'll see a 16 there. That means 16 grams per mole. Okay, so molar mass would be that amount, the grams per mole. And then you can figure out the amount of moles that you have. And then we looked at a collection of particles, and we wanted to figure out, given the temperature, how much kinetic energy a particle has. And it's just related to the temperature. So the average kinetic energy is 3/2 kT. That has to do with 3 degrees of freedom. Each degree of freedom has 1/2 kT of kinetic energy. And this is Boltzmann's constant. This is not the spring constant. So here's Boltzmann's constant. 1.38 to the minus 23rd joules per degree Kelvin. Oops, I shouldn't say degree Kelvin. Joules per Kelvin. You don't have to say degree Kelvin. You just say Kelvin. So, if you put this in for Boltzmann's constant, you see the Kelvin cancels out, and you're just left with the energy in joules. If you'd rather know the speed, kinetic energy is 1/2 mv squared. So the RMS value, the root mean square value of the velocity, again, put in 1/2 mv squared for this, do a little bit of algebra, we came up with this. So the speed is just related to the temperature and the mass. Excellent. The last thing we looked at, one of the last things we looked at was the ideal gas law. This is sort of the physics version of it. PV, so pressure, volume, is equal to the number of particles, Boltzmann's constant, times the temperature. Maybe the chemistry way of looking at it is PV is equal to nRT. This, if you're in chemistry, this is probably what you're more familiar with. Here, N is the number of moles, R is the constant down here, and then same thing, T is temperature. We also looked at in class some ideal gas processes. What I mean by that is, say you have a container that has a fixed volume and a fixed amount of particles in there. You could see what happens. You heat it up. What happens to the pressure? That sort of thing. So we could look at it like this, maybe. So let me grab another piece of paper. Ignore what's on the top for the time being. So again, if N is the same, and we have Boltzmann's constant, which is the same, you would have something like PV over T, and you can go P1 V1 T1 would be equal to P2 V2 over T2. And again, that's keeping the amount of particles the same. Boltzmann's constant, of course, is the same. So if you were to increase the temperature here, what happens over here? Again, the volume is going to be staying the same in this case. If it's just a solid cylinder, you can see what happens to the pressure. So yeah, if the volume is staying the same on both sides, you just have P1 over T1 is equal to P2 over T2. And you can see, again, how this thing works out. Okay, so by ideal gas processes, that's what I mean. Take a look back at that. And then the final thing was, the heat required to increase the temperature of a substance. So Q, that's the amount of heat. In this case, I mean, we had Q for volume flow rate, but you have to know the context of what you're talking about. So Q for volume flow rate, this is not the same Q. This is heat measured in joules. It's the mass of a substance times the specific heat. So C is the specific heat. This is not M sub C. This is mass. Actually, let me write it out. Mass, specific heat, and delta T is the change in temperature. Okay, so take a look back at those problems that we did in class dealing with this idea of heat and temperature changes. Okay, hopefully that was helpful. Again, look at the practice tests, the actual tests. We've had a test over everything except fluid dynamics, which we did some problems in class, and this thermal properties of matter, and we did some examples in class too. So that's what you have to look at, those problems we did in class. Okay, and again, the whole test is not focused on the last 2 days or something like that. So you probably see one problem from chapter 12 and maybe one problem on fluid dynamics. Okay, talk to you soon. Good luck. Bye-bye.